Okay, good morning, everyone. I hope you can hear me. Please someone to confirm that. And can you hear me? No.
Yes, we can.
Yeah. Okay. Okay. So we have finished. The last lecture saying about sonars and more or less about this picture, showing the directions, how the energy is emitted. So we can see that approximately you have the high energy beam going more or less like that, and everything what is in this range in this angle, let's say, whatever appears here also these directions or this and so on. General view, depending on the shape of the sonar, the cover that they use, the angles can be slightly different. Also, the proportion between the highest peak and the smallest ones can be also different depending on the shape of the sonars and the shapes of the external covers. There are some special solutions of how to shape the beam to make it more narrow or wider, just to somehow deal with this property of the sonar. And just as some problems that are related with it. So firstly, there will be some questions to you as well. So one thing that we said, okay, so we have a beam like that, and whenever an object is like here, or in the second situation, the object is here, they will be detected exactly the same. So the sonar will return this distance as an output. So the answer will be the same, and we are not able to detect exact direction where the object is. Sometimes it is a problem, sometimes it's not. So if you want to make a mapping for the robot, for example, you would like to have a precise location of the object. But for example, if you park a car, you not necessarily are interested in exact location of any obstacle. You just want to know that there is there is an obstacle in a certain distance. And if it's a little bit to the left or to the middle or to the right, doesn't really matter. And that's why it was a popular solution in the supporting parking for the cars. Okay, and that was something that we finished last time. Some more remarks. When you imagine that we have a wall like that, and we have a sonar located more or less in that place, and it sends a beam of that white. Okay, it should be a bit symmetrical. So let's go that direction. And let's say the center is more or less here. How do you think, what will be the distance that will be measured to the obstacle? The left, middle, or the right one? What do you think? Well, we said that will be the closest one. So most likely you will get this distance as an answer. Of course, if the direction of in which it is reflected will hit the sonar. That is another issue. So that's something that happens here. So the distance is not the distance in the middle, in the direction when you look, but the closest distance between within the beam. What happens further? You probably remember the laws of reflection. In fact, in this situation, with that looking at that angle, probably nothing would return to the sonar because the beam one would reflect this direction, this one would reflect this one. So the reflected beams do not return. So to get it back, you would need to have a more the beam more or less like that. So then you get a reflection that, let's say, goes in this direction, so that it covers also the sonar. What else may happen? When you have a situation like that, you have the right angle. Okay, not the best version of that, but if we have the right angle and we send a beam from the sonar, it will reflect more or less like that. So the distance that you get is not the distance to the wall, but it will be just a total distance of this part, this part, this part, divided by 2, of course. And when you look a little bit closer to the geometry, you will find out that this will create a virtual wall visible by the sonar that will be more or less like that. Because this half of the distance is equal to that part, and this part is equal to that part. So that will create that kind of the virtual wall. And when you change the direction of your sonar, when you look at this wall, you will get that image until you finally get to the point when the reflection will be closer reflection will be direct to the sonar, and then you will have that kind of the line and that kind of line. So just to have it more visible, so that will be the answer if you rotate a sonar close to the corner. So a little bit of the wall on both sides, and instead of the corner, you have something, a third wall of the width depending of the beam width and in the distance of the real corner. So that's more or less where this wall appears. So the image is completely not looking like a corner of the room, and you need to know that you need to interpret it that well, that as a corner. So those are the problems with ultrasonic ranging. Anyway, as we said, the width of the beam can also be useful, especially when you look at it as a detectors, because it allows you to cover a wider range of angles with a single measurement. If you have the sonar like we had it here, like you can see that it's like 10 degrees here, so it will be like 20 degrees cover. But you can also have a sonars that have this middle peak of the width of 30, sometimes even 60 degrees with proper shaping. So you can cover high range and detect that there is obstacle if you only want to know that there is obstacle, not necessarily the exact direction of it. Okay, so those are the sonars. The main advantage of the sonars is, of course, their price, that they are quite cheap, and that's why you can use them even on the simplest robots. Then next elements to detect the distance are the time of flight rangefinders based on light. It's usually in infrared light, not visible for a human for close infrared. And you can have either simple devices measuring in a single distance, or you can have the laser scanners that we show on the way. So, what is a main problem with measuring the distance based on light? As you remember, the formula for the distance is that the distance that we go through is like 2d is equals velocity times t. And if you use light, you have the speed of light. And you can realize that the time that you need to determine, that you need to measure becomes very short with that value. So we need to be very precise with measuring the time. Of course, there are some methods to deal with. So if you shape the instead of using the same excuse me the same intensity of light, you shape the wave with additional change of amplitude that with a different frequency, with a lower frequency. So in fact, you can use the not only measure not the speed of light, but speed of this created beam by yourself, wave by yourself, and then you can reduce that problem. What else you can do? You can also use the approach with the phase shift. What is a phase shift? Just before returning to the proper formulas, just a simple idea. So you send when you send a beam with a like a sinusoid wave of certain frequency, then it goes to the objects and then it returns. But it returns a little bit shifted in time. So we have like the time shift in here. If the shift between phases was 0, then you would get the simple answer, like you get the first beam and the second, and it's simple, 2 times the original wave. So, but if the phi is not 0, the sum of the you get the following formula: this plus sine of omega t plus phi is 2 times cosine phi over 2, and here is sine. It is the same frequency, but a little bit change shift. But what is important, the amplitude here is not 2 times the original amplitude, but it is reduced, a smaller one reduced depending on the shift. So when the shift is 0, you get 2. When the phase shift goes towards, in fact, it's pi half over 2, so pi over 4, you get it goes to 0 until in fact the value the returning wave can cancel the original. So as you can see, knowing that, you can, knowing the change of the amplitude between these two signals, you can measure the phase shift, and based on the phase shift, you can measure a distance. Of course, it comes with some additional issues, because when you look at this wave length, this phi, in fact, is repeated with the period of 2 pi. So you must know if you hit the, if you are shifted by only by phi, or you are shifted by phi plus 2 pi, or 2 pi times k. So this will give the same amplitude change, and of course you need somehow to deal with it. But anyway, it can simplify your approach, because you do not measure the time anymore. You can measure the change of amplitude. So that becomes a little bit easier. In fact, the formulas get a little bit complicated, because the returning wave is not this, doesn't have the original amplitude of the first one. It is it has some reduction ratio here, with this r smaller than 1, because the amplitude of the wave decreases as depending on the distance. So the formula, in fact, is a little bit more complex, but that you will find it further. Okay, so how does it work in hardware? So you have a transmitter that goes through a semi-transparent mirror, goes to the target, and but at the same time it gets reflected to the phase measurement. On the other hand, you have the reflection from the target returning back, and the second beam goes again to the phase measurement. And here you compare both of them, transmitted beam and the reflected one. Okay, you get the idea, and that's the solution that we get. Quite simple with the phase measurement, but with this ambiguity of the range. So in fact, you get the same solutions every 2 pi times the length of the modulated wave. Okay, so that's the main idea of the measurements, and it is used in different types of measurements. As we said, we have the rotating scanners, and you could see the families of the different scanners. One of the project group who were already testing SICK and Hokuyo. Well, it's not exactly this. Okay, it is similar to this one, but not exactly the same. We were on the yesterday seminar. We are also saying about this solution with the external motor, as we said, a cheaper one, but more prone to errors, mostly because of here this mechanical unit that appears in that point, and it is vulnerable to any external conditions, some dust, and so on. Okay, so but maybe looking from the outside is not that interesting. You can see it in the laboratory anyway, but it's a bit more interesting to see of what's going on inside. And inside, what you have here is this this laser beam transmitter, but also the measurements. That also goes in the upper part. And at the bottom part, you have a mirror that is here. The mirror is rotating, and you have the motor that is rotating the mirror. And if you want to recall our previous lecture, here you will have the plate of the standard optical encoder. So that will be a metal plate with the holes in it. You can, I hope you can see it, that stabilize the velocity. So the mirror rotates always with the same velocity, and the exact direction in which the beam is sent is therefore known very well. In fact, it was for a long time this company, SIG, that you can find here, and that for a long time they had a monopoly in laser scanners because they were the only company that could do that have solved practically the two problems, the main problems here. So how to stabilize the velocity for a long period of time to get very precise measurement of the angle. In fact, this scanner was able to measure with the precision of 1/4 of the degree. And the second way is how to be able to measure a distance with the precision of just single centimeters and in the range of up to 20 or in good conditions even 70 meters. So long range and high precision measurements. So that's how this scanner works. And maybe the last solution, a similar one, but not using the visible beam. They are also time measurement or distance measurement using the electromagnetic wave is also used in beacon-based localization. When you have certain radio transmitter that sends some radio signal to the receiver. And again, sending a wave, you can, knowing the delay time of the movement between those two transmitter and receiver, you can measure a distance, and partially this approach is used in GPS. It's the first of the method. That's why we're ranging. So you have the data that is sent from, or the beam that is sent from one element from transmitter and being received on the other side. But to be able to measure a distance, you need to know exactly the time when it was sent. So you need to time of transmission, and you need to know the exact time of receiving. And as you probably know, in GPS, you have these satellites going around the Earth, and each of them needs to have a very precise atomic clock exactly for that purpose, to know exactly what is the transmission time and to have exactly the same time of the transmission from each other satellite. If you know exactly the time and you know where you received it, you can measure the time difference and make the measurement of the distance. Maybe you can have a question why at the receiver you don't have an atomic clock, and how do you precisely know the time of the receiving in GPS? Well, in fact, you do not, but you know you use a slightly different approach, because you don't have an absolute time in here, but you measure data from different sources, and you use the difference between the sources, and then you don't need the precise receiving time. You just need to know, when you know how these objects are distanced from each other, and they already transmitted by themselves, then you don't need to know the time here. You need to know, you can calculate it from other methods. But we will not tell about this localization. It's in fact a part of the completely different course. Okay, that was one-way ranging, having the problem with the exact time measurements. But you can also have a two-way ranging when you have the transmitter, that is in fact transmitter and receiver, and you have a transmitter and receiver on the other side. And the measurement uses bidirectional communication. So in fact, a single measurement works more or less like that. You initialize measurements. It goes from the, let's say, side A and side B. So you have a side A, you have side B, and you have the timeline of both. So you send the first signal, then it's processed somehow in here. It takes some time, and then you send it back. You usually need to know how much time was wasted within B, so you need to subtract it. But on the A side that measures the distance, you know where you send the signal and when you received it. If you also know how much time was spent in B, and B can send this information even within the reply message that goes back, you know that it is like time that is proportional to distance, and so you have like a time total, and that you have the time that is B. So the time of the referring to the distance is in fact the time total minus time spent in B divided by 2. And again, you use the velocity of the wave to calculate the distance that you get. And this radio localization, radio beacons are also used for measuring the distance, sometimes using this simple approach, sometimes they duplicate it, so they for a single measurement they make like twice this two-way ranging approach, just to reduce the error, but also to inform B about the travel time, because currently in this situation only A knows the distance, B doesn't know that, it doesn't have enough information. But if you make again a similar process again immediately after the first one, then also B can get information about the distance, and it will be informed on the both sides. So those are also there are also such solutions, and in fact, if some of you are interested, quite popular recently, Decawave system, small modules that you can use for exactly that purpose, using this method, using radio wave in so-called ultra-wide beam. So not working on a single frequency, but on a wide range of frequencies, to have the increased robustness to reflections, noises, and external sources of other radio waves, in fact. So quite an interesting solutions that also worth to be known. Okay, so and that will be the end of the distance location based on the distance sensor directly. And the second part for today is the vision systems, and that will be the basics of the vision systems right now. Just need to switch to another part of slides. Okay. So when we say about the vision, we will think about two main approaches. So 2D vision and 3D vision. And we'll say a little bit about both of them today. Of course, it is because it's not a lecture about the vision systems themselves. So we will not say about the how the color is created, how the matrices works, and how the image is at all registered. Let's assume that it somehow works. Of course, you can have very different vision systems using standard visible light. You can have infrared light. You can have some color filters that eliminate certain range of waves. So of course there are lots of technical things how to collect the image, but let's say that we will skip that, and we will assume that you already have the camera, no matter how it exactly works, and but we are trying to interpret the data that we get on this from these cameras. So first thing, just to know what happens in fact both in 2D and 3D vision, in both of them the basic acquisition of the image is two-dimensional. So you get a matrix that is like a plane. It's usually a grid type. You have some rows, you have some columns, and it's just two-dimensional plane. But the world outside that we are trying to measure and to observe is in fact three-dimensional. So you need to make some kind of a projection and remove one of the coordinates. From the 3D to the planar image. So the basic three types of the projections are firstly the orthogonal projections. So if you have the matrix, you have an object somewhere here, so the object is transformed always with the parallel lines. So the object on the image will have the same size independently of the distance between the objects and the, let's say, the film. So that's always the right angles in here. It is very useful type of the projection. It makes all the analysis very simple, but in fact it's not very easy to get it. Only in certain conditions, for example, when you have the telelens you can get something that can be interpreted as the orthogonal projection. What you normally get is the perspective projection, or sometimes it's interpreted as a pinhole camera. And that you probably know from some physics and optics. So you assume that there is an observation point, this eye of the related with the film plane with the focal length, and you have some objects that is here, but the collection of the image is done through the beams that all go through this eye point, so the focal point of the camera. What generally means that the image that appears on a film here scales the original object depending of the distance to that object. So the same image here will correspond to the object like this, or to the object that will be farther and that will be bigger. And this kind of regular perspective, both the one that you probably got on the lessons of physics and maybe on the lessons of arts of how to show the perspective. One more special interpretation is that the spherical projection, when the assumption is that okay, we get more or less the same focal point approach, let's say direction, but the interpretation of the film plane is not really flat. It is a part of the sphere. Of course, you will not find it in regular cameras, but it is the way how, for example, three-dimensional scanners return their values, because while here you get the x and y position on a plane that corresponds exactly the x and y position of this flat surface located in some place here. In this place, you usually get the interpretation of the cells as an angle, angle in horizontal plane, angle in vertical plane, and so it's it in fact reflects to the beams sent into different directions. When the film is a small one, in fact, they are quite similar, so they can be easily transformed or simplified one to another. But if the angular range of the measurement is higher, they will be more different from each other. So that's something to take care of. But of course, most of the cases, and when we talk about regular cameras, we will say about the perspective model and this standard approach that is here in the middle. So from now on, we'll concentrate on this approach. Okay, and so when we start of it and we show this image, we have an object, we have this focal point, we have the film. So the question that appears, how to deal with the numbers that will appear here, and especially with the coordinates, because it will show up that you have quite a few different coordinate systems that will be useful in this situation. Okay, first question is what can be this coordinates frame, and the second one, how to transform them. And yeah, that again will be questions that I will ask you, and maybe you will try to answer. So firstly, we can have we will have the coordinate frame that is real world coordinates. So we have the object, and the object is located somewhere. Maybe I need some place for drawing. So we have this global coordinate frame. We have this X, Y, and Z, and this is our world. And somewhere in this world we have the objects that we are interested in. That's the first coordinate system that we have. But also somewhere in this world there can be a camera looking at the object. And this camera will also have certain world coordinate, but also except being in some world coordinates, it also will most usually have its own coordinate system, usually with z-axis toward the objects and y and x, more or less like that. And that will be the local coordinates frame associated with the camera looking at the object, because the objects visible in the center of the camera can be we can shift both of these objects and the camera both of them we can shift around, rotate, and the image of the object on the camera may remain still the same in this local coordinate system of the camera. Okay, so those are first two. So we have the world system and camera system. What we have more, there is a film coordinate system, which is in fact the effect of the projection. The effect of the projection of the x, y, and z coordinates of the object that we have here. So here we have x, y, and z from the camera system, and they are projected somehow. So they are projected somehow to the position of x and y on the film plane, and this projection depends on the focal length. So the position of the focal point with respect, or the distance of the focal point from the focal plane. Okay, so that's the film, and the important part, it is the real value, real number. So having also the fractional part, and then this x and y coordinate of the object is a part of a pixel that is located in a certain row and column, and this one is integer. And in fact, it is a positive integer. So it is the number of the row and column of the image that you get here. So the raster image from the film. So now the question of how to transform this element to each other. How to get the word transformation between world and the camera coordinate system. So how to transform between this and this. Just to recall, no sound, no answer. Last semesters we were saying about the transformations. We can have here world, can have here camera, and we can define these transformations in a standard way as there are some rotation and the translation 0, 1, and we can simply define it as that's just a transformation between two different coordinate systems, and that's exactly what we are doing, calculating the kinematics of the robots. So the global coordinate systems like a base of the robot and the local coordinate system of the camera as somewhere in one of the joints. So that's exactly the way that we were doing that. So of course not the only approach, but the one that you should know. 4x4 matrix, rotation part, translation part, and then you can transform the position of the objects between local with respect to the camera and the global with respect to world, depending on the position of the camera. So those are just the transformations that you already know. But what happens with the transformation between camera and film? What you need to know? Okay, that's just a projection. That's just a perspective projection, and what you work with are just this. You have, sorry, it should be perpendicular. So you have, for example, the x value here. You have the z value here. You have f here, and what you know is like that. This small x, okay, that will be more difficult to see, but small x divided over z is equal the capital X divided over f. So that's simply the projection that you get in here, just from the Taylor's theorem, from the triangle that you get. And of course, the same will work with y part that you get. So the y part, y over z, will be equal, so y will be y over f, and then you get the answer as well. That's the type of the transformation that you get in here. When you know x, y, and z, you can easily get x and y. And if you want to make opposite, so if you know x and y, how to get the position in the space? Someone can answer that? So we already shown how to get the film projection from the camera. Now, if we know the film positions x and y, how to get the position of the object in space? So the second arrow in here. Okay, no answer again. But, well, the proper answer is, well, it's not possible, because from this part, you know X, capital X, you know F, you know capital Y, and you don't know X, Y, and Z, and you have only two equations and three unknowns. And yeah, it's not possible. And it's quite clear also from this drawing that we had earlier that, okay, if you only have the image on a projection plane on a film, you don't know if it's this object or this object or even the object further. So you have the relations between the elements of the objects, but you don't, not knowing how far the object is, you don't know which size you need to choose. And in fact, solving this part will be one of the issues of using the camera for interpreting the world that we will be talking later. Okay, and what happens last? We have the film to pixel projection, and yeah, and this one it becomes quite simple. So if you imagine that you have division of the image more or less on equal grid. So if your point hits, for example, this position, you can just round it to the proper integer value and get the answer, how to transform the film coordinates, which are real, to the pixel coordinates, which are integer. What to do to the other direction when you want to, so again, film to pixel, that's the easy part. Pixel to film, there is a difficulty. The difficulty, and it results from the fact that one pixel, like for example this pixel, corresponds in fact to a quite a range of film coordinates. Yeah, so it's not a single point as you had here, but it's all square with its interior. So the pixel to film, you know how to do that, but in fact you don't get from a single pixel, you don't get a single point on a film, you get a square on a film. And if you want to go from the beginning, from the pixel to the camera, so you have this square in unknown distance. So a single pixel, let's say in this position, can be a bigger square in that position, and so on, and even bigger when you go further. So the transformation in one direction is quite simple because it is uniform, but going back, you need to solve certain ambiguity and solve certain how to choose a point from the square, or how to detect the distance to determine the size. Again, how you can solve it? Maybe one of the ideas that comes quite obvious. We said that if you don't know the distance, you don't know what should be the size of the objects, and with the bigger distance, the objects will be bigger. But if you want to use it, for example, for location using the cameras, if you already know what is the size of the object, then you can determine the distance. And then knowing already, for example, the size of the object that is the size of the object in real, and knowing its proportion between the size in real and the size on an image, you can determine the distance. And in fact, again, referring to the projects that we have, a group that was calibrating a robot, the Fanuc robots, you were using the grid with the dots, and they were different grids with the different distances between the dots, and you needed to provide these distances from the reference image to the system so the robot could calibrate. And it was exactly this. You were informing what is the size of the objects that are in real, so the robot could compare the image of it and determine the distance using these values. So that's how it roughly works, but we will be going to the details. Okay, so those are just exercises of how to do that, and yeah, and the transformations that we have already shown. That's just a nice review of what we had after the transformations. And when we combine the transformation between the okay, one more thing that I skipped. As I said, when you transform from film to pixel, you need to round to the integer. That's quite clear. But this rounding depends on the resolution of the image that you need to get. But another thing that you usually need to remember is that, okay, when you use the film plane or the film coordinate system, you usually select this point, the center of the axis of the image, as 0. But in fact, when you get an image from the camera, the 0 is somewhere here in the corner. And moreover, you were probably used, as everyone, that you have X and Y positions in the coordinate system on a plane like that. But the computer graphics they selected, they have X, but they have Y to the bottom, yeah, so going down. So instead of right-handed coordinate system, they use the left-handed. There are some things that you need to remember with these transformations and interpreting the image, not to get the image upside down. But okay, so what happens here? We already had this part, and then we transform the data to the pixels in such a way that our pixels data are the transformations from the camera to film, and from film to the pixel, px and py are just resulting from the resolution of the image. Cx and cy are the center of the image. So again, a transformation has the form of the matrix. This parameter that is called W is in fact the distance transformed through the focal length, simply. Okay, so those are the two main formulas that you need to remember. So transformation from global frame to camera frame using the standard transformation matrix, and the camera to pixel transformation using these formulas. Okay, and yeah, and that was at that point we finished some things that are simple and linear and based on a nice transformation from the simple things like Taylor's theorem, and we get to the problems. The problems that we get are that in reality it doesn't exactly work like that, because the whoever seen how the lens of the cameras are built, so they have some glass, well, recently plastic elements in shape of some cylindrical or spherical. More or less, the light goes through several lenses before getting to the point, and it's somehow shaped, either this or this version of the lights, before it gets projected to the film. whatever happens here causes that the image of the standard square grid will not necessarily be a square grid at the end. And we get something that is called the distortions. These distortions will just spoil these nice formulas that we had before. Generally, we have these three types of the distortions. The barrel distortions that mean that the elements that are farther from the center, like here, instead of being, well, let's say like that, they are a little bit closer. So that we get the distortion that, depending on the distance, so that is like a square of x squared plus y squared, that there is some distortions that the distance is smaller than it should be. And it is visible in such a way that the corners get a little bit closer, and it starts to look more or less, so this grid looks like more or less like a barrel, and that's how the name is. This is the source of the name. Then you have the opposite type of the distortion, when the distance, in fact, is bigger than it should be, and you call it a pincushion distortion, and yeah, looking more or less in that way, just an opposite to the barrel. And the first two are still you can more easily deal with them because they are uniform in different directions. So there are some methods to apply the corrections in these two methods. This one is a little bit more difficult. It's called the Mustard's distortion, which is a kind of the combination of two of them, when you have a partially barrel distortion in one axis and the kind of a pincushion distortion appearing in other areas of the image. Yeah, and that becomes more difficult. What in fact it means? All these distortions are just the elements that break these equations that we have here. Look at the final formula that we got here is a simple linear transformations. All the parameters here are just constants. So you just scale the distance here through some constant matrix to get the image. When the distortion appears, the transformation is no longer linear. There appears some quadratic elements to be included, or higher order elements that can appear as well. Probably when any one of you used a camera, especially with zoom, you can observe that you get this the barrel distortion that going from the short to the long length of the zoom of your camera. You can go from the distortions going from one type to another, having a perfect image or close to the perfect image somewhere in the middle of this, well, not in the middle, somewhere between the two different focal lengths of the image. So that's more or less how the zoom, especially zoom lens, are created. That they have, well, just a single point when it's okay, and going shorter or longer focal length, you get either of the distortions. Okay, so how to deal with them? As I said, the barrel and pincushion distortions have the form resulting from some square and higher range terms coming from the radius, from the center of the from the axis of the image, and it generally looks like that this displacement of the objects in x and y, or displacement of the point in x and y, depends of the real x and y, and some coefficients that you have here multiplied by the radius in even powers of the radius. And as you could see, that the barrel distortion is when these parameters are smaller, and the k parameters multiplying here are smaller than 0, and pincushion when they are bigger than 0. And the masters that when the signs of this case are somehow mixed. Okay, what you can do, of course, if you need a very precise image, what you usually need to do the compensation of the distortions. So you can take the standard procedure is taking that kind of the image or the checkerboard type, observing it with the camera, recording the image, calculating the points, checking their positions. If you know the positions that there should be, you can calculate all these coefficients for the corrections. Yeah, and then you can correct the image so to get something closer to the standard perspective or pinhole projection. So that's what people usually do when they can. But as we said, the zoom when you have the zoom lens, the problem is that depending on the current focal length, the parameters may change. So in fact, we will have the fixed fixed focal length camera, fixed focal length lens. You can just determine these parameters and use them for the corrections, and it's not so difficult. But if you have a smooth zoom on the range, these parameters will change, and then the corrections, it becomes more difficult. Probably you can do it for certain values of the focal length and then approximate the other parameters between them. Okay, so that's the way of dealing with the distortions. Of course, you need to remember that these radial distortions that we have that presented here, they are the most typical, but you can have other types that are not so simple to show, especially when you have a simple lens that are non-professional lens. So they can be other types that are not so easy to deal with, and then you need to find some own solution if you need to normalize these images with other types of the distortions. So those are not the only ways, but usually most typical. So if you can deal with them, you will remove a big part of the error that you have in most cases. Okay, so all the other calculations that we will be showing will assume that you have already done the corrections of the distortions, so that we returned to the normalized image. And what we have, we can show the some applications of these vision systems, not to interpret the image. As we said, interpreting the image is not for this. It requires a completely different lecture with the computer vision, but with the measuring the distance, that is the main point of the robots that we are using here. So how to use the vision, the camera, to measure a distance? You can find the applications in different types of sensors. One of the basics of the basic one, quite often used in, for example, robotic mini sumo competition, is the infrared proximity sensor, more or less the one that you can see here by Sharp. And this proximity sensor operates more or less in that way, that it has some LED diode projecting the infrared beam in one point, and it has the camera. The camera, which is quite simple, it may be even not. It doesn't need to be even two-dimensional. It can be only one row and multiple columns. So it's a so-called line camera. You just get one line of the image. But what you can see, what happens here, that when it reflects to an object that is close, the reflections goes a little bit further, and you will notice the object here. When the object is further away, the reflections will appear here. So knowing the point of the reflections, you can estimate or calculate a distance of the objects from the LED. Quite a simple solutions. The problem with the sensor is that it's not linear. As you can see, the response of the distance is not non-linear. You have higher precision in the close range. So when you move the objects here, the shift of the pixels is bigger. When you are farther away, the shifting of the same distance, let's say going closer here and going closer, the same value here, in this point will mean a bigger shift, and it here will mean a shorter change. So that's exactly what you see on this graphic. So so it's like you don't get the same resolution of the distance measurement for a whole range. In fact, it's changes quite a lot. And as you can compare, for example, the change between 3 and 2.5, this is an analog output, so you have just an output in volts. So change between 3 and 2.5 volts means more or less like 3 centimeters in the range here, so between like 7 and 10, and changing from 1 to half in this range corresponds to, well, let's say 40 centimeters. So quite a lot. As you can see, a very high change in the precision of the measurements. Again, if you want to know how the change is calculated, just an exercise, you can see how this, in fact, this reflection works, calculating these distances, and how this point of the projection depends on the distance from the objects. Just simple formula from the triangle analysis. Then a similar approach that can be used is the approach used in a stereo vision. And you have here an example of the stereo camera, but for example, those of you who use the RealSense camera to work, the camera also has the stereo vision part. The work is very similar. The operation is very similar to the IR proximity sensor, with one exception. On the previous page, the LED was projecting in a single direction, and you already knew it. And it was in fact active sensor because it was sending certain beam that was getting reflected, while the stereo vision is passive. So we don't send anything, but you just measure an object. So you detect an object, you see it with two cameras, and in one camera you see here, with the second camera you see here, and comparing a difference between the images of the two cameras and knowing a so-called base, so the distance between the two focal points, you can calculate where the object is, because, for example, if we have the second object here, you could see that it would be on this image, it would be somewhere here. On this image, it could be, well, wouldn't fit on the image, but let's say if it was still there, the shift will be different. The difference between the image on the left and right image will be bigger, and we can calculate that the distance is smaller. And yeah, that's kind of an obvious observations. In fact, that's the way how human eye works, and you can you can look at some objects that are closer to you and further to you. Close one eye, open one eye, close one and another, left and right, and see how the objects move. So you can just practice and see that indeed the objects that are closer, they shift more between left and right eye, and the objects that are further shift less. Okay, and yeah, and this the way of the calculating is more or less the same. The only problem, well, we can say only, but in fact it is just a difficult one to solve, is that you need to detect an object, and you need to know that it is exactly the same objects. So if you have a unique, just one object that appears, and that is a characteristic one somewhere in space, for example, like here you have this ball, you have this S, it's quite easy to recognize it and compare two images, find it on left image, find it on right image, and then compare the results. But if you look, for example, on a uniform plane, like you look at the wall painted in the same color, without any characteristic point, there will be nothing that you can find on the image to compare one to another. So so this method works well when you have some unique objects. If you cannot recognize anything characteristic, you have nothing to compare on the left and right image. If you have only white image on left, white image on right, you will not have a distance measurement at all. What else can disturb? If you have some uniform pattern of both on the view, let's say we look at this checkerboard that we are talking about, then again, it's quite difficult to, or it may be even impossible to determine which characteristic point on left image fits to the one from the right image. And if you mistake and take not the correct one, then the calculations of the distance will not be correct. Okay, so those are just the observations that we have, and yeah, and those are here we can see more or less how the how this method looks like. We have some space in here. We have a left image, right image. You can, for example, notice the lamp and the sculpture. There is a difference between this left and right image. The lamp has moved a little bit more, so it means that it's most likely to be closer. But what happens when you make the comparison? The results that you usually get from that is the image to the left. So there are some sometimes incorrect fitting of the objects. Sometimes you get some blurs resulting from the shadows casted and so on. So there is not a very high precision of this measurement of the distances. Usually that requires some additional processing to really eliminate all the kinds of the noises and to get the image right, like the one to the right. And what can be these artifacts and problems? So some kind of the smearing that's usually related with some shadows that can be cause some mismatch between the points. So you match the point with the point that is a little bit different. What can be a reason, for example, of that is when you have these two cameras, let's say like one and the second one, and the view of the second one, and you have an object here like the first one, and you have an object like that, some uniform object in here, and you make a projection of this shadow, this object to this plane, and you make a projection of this line, and you make a projection of this point a little bit next. And when you look from this camera, you have a projection of the object here, but this uniform object, you notice just next to this, you notice another part of the object in the back. And in fact, you cannot distinguish between this point, well, between this point and this point. They are all the same. So this smearing may result with the fact that you are matching the point to the left instead of the point a little bit to the right, and you are treating it as the same point in here. So that's the reason of the smearing. There can be some dropouts. So some points may be not visible. Yes. So you see something from the right camera, you cannot see it from the left. So you cannot match the objects. And opposite the same. They look from the slightly different points. So they just overlap. Then another part is the range of range resolutions, and that's the thing that we are showing with this infrared sensor. Yes, so the resolution drops with the range, so the precision of the distance measurement here drops as well, and again the approximation of the distances. So the objects that can be a little bit away but being far from us, maybe the approximation of the distance may give you the same result because of the drop of resolution. And the last problem, resulting not from the image itself, but from the algorithm, is the processing. Yeah, as we said, you need to match the points. So a lot of the quality of the stereo measurement of the distance results from the method of detecting the same points on two images, and if the method is not good, then also the results of the final processing is also not so good. So just to summarize of what you want to get when you are trying to use the vision system, as we said, we try to use it as sensors for finding objects and measuring the distance to objects, but we are not saying about the interpretation, about the finding any other properties here. So just using it mostly as a distance sensor and collision detectors. What are the general properties? Okay, image is usually lots of data to process. As you can get with the high resolution camera, you get like 4 million points, more or less 30 times per second, and then you need to do something with it. When you use the stereo vision, you need to even double it. So that's lots of data to process. As you already said before, for example, from sonar, you can get like a few measurements per second, maybe 10, maybe 20. With laser scanner, you get, let's say, about a few thousand single distance measurement per second, while in camera you get millions of points, and of course processing that requires some much higher processing power, much better microprocessor than the other sensors. The vision is also vulnerable to ambient light. So especially when you have a strong sunlight, the sensors like infrared detectors, you may not, well, what is important in here, you need to see with this camera, you need to see this reflection point on an object. So if the object doesn't reflect, or it reflects some sun, you may not be able to detect that point, and you will not able to use this for measurements. Also, different changes in light in stereo vision can also influence the precision of the measurements. Lens distortion, that we already said, easier to compensate with the fixed focal length, but increased in zoom lenses. And the fact that we have non-linearity in most cases, that again influences this resolution part that we are saying before, or also related with the distortion. What else? We have also some problems that appear when we use stereo vision. The image that we had here was quite kind of ideal. So we had the camera that are on the same line, and they are exactly parallel. But if the axes are not parallel, then the calculations are more complex. And if these axes can change, they are somehow movable, then the problem is even bigger with normalization of that calculations. And the wrong feature matchings that we already said about, that you need to detect correctly the same features on the left and right image, and if you do not, all the calculations can get wrong. Yeah. And so those are the problems, but of course you of course get a lot with this sensor. So if you manage to deal with these high processing requirements, you get a lot of data that you can use. So when you have the simple infrared sensor, you just get a single point, or if you have a single sonar, you have just one single distance somewhere around. While using a HD camera, you get those 4 million points that we set, and yeah, each of the points can bring you some information about the surrounding of the robot. So you are getting much more information, and as long as you can process it, then it simplifies and increases the capabilities of the robot that you have. What is also important, why we like using vision, is because vision is also the basic way of perception of the world for human. And that's how our world is built. So if we want our robots to work in the same environment with humans, we have already lots of visual information that is especially prepared for humans, for example, some signs, writings, and so on. And if we don't want to change and create a special environment for the robots, we want the robots to be able to perceive the same types of the information as human do. So it may be less important in the special environments like industry, but if we say about the robots for the social robots, the robots that work with human and that will appear in our regular environment, then the vision becomes important. Okay, and that will be the end for today. If you have any questions, please ask. If there are no more questions, next time we'll say about special applications of this vision system. So about using something that is called visual servoing. Visual servoing is like a direct control of the robot using the vision without supplementary calculations of the coordinates. So the thing that will be useful to recall for that is first the transformations we were talking today, but also the previous semester kinematics and the Jacobian elements, what it is and what we meant by the Jacobian when we were saying in the last semester, because those will be the things from the theory that will be needed for the next lecture. Okay, if there are no more questions, then thank you. And we are going to finish. Okay, goodbye.
Thank you, goodbye.